All right, welcome back. So this is an ALEKS topic that's called using the ideal equation of state, and there's two different versions of this problem that I'm going to go through. The first one is sort of a more basic, simpler version, and the second one is definitely more involved, so stick around for that. So let's get into this problem. The first thing we're going to do is organize the information that's given. We're going to think about what equation we're going to be needing to use, and then basically just apply it. So the first thing I'm going to be doing here is just organizing the information that's given. It says sulfur hexafluoride gas, so we're talking about some sort of gas, is collected at 19 degrees Celsius, so that's a temperature. So I'm going to start by writing temperature equals 19.0 degrees Celsius in an evacuated flask with a measured volume of 5 liters. So that's our volume of our flask. It's going to be 5.0 liters. When all the gas has been collected, the pressure in the flask is measured to be 0.410 atmospheres. So that's obviously going to be the pressure. Pressure equals 410 atmospheres. And then it says calculate the mass and the number of moles of sulfur hexafluoride gas that were collected. So definitely I'm going to be looking for both of these things. I think I can figure out right away that we're going to be looking for the moles first. And then once we know the moles of that sulfur hexafluoride, then we can figure out what the mass of that should be. So this right away is pretty obviously to me going to be a PV equals nRT type problem. This is our ideal gas law. We've got our pressure, we've got a volume, we've got a temperature. The R is going to be our universal gas constant. We'll get very familiar with that. And I'll be able to use this equation to solve for the number of moles of gas that would be present under these conditions. That's essentially what we're doing here. Now, one really important thing, I want to convert this 19 degrees Celsius into Kelvin. Anytime we're using the ideal gas law, we really want to be using Kelvin. So this, I'm going to add 273, is actually going to be 292 Kelvin. That's going to be the number that I want to use when I use my ideal gas law. Basically, I'm just going to plug everything in. My pressure here, 0.410 atmospheres. My volume, 5.0 liters. That's going to equal N, which is what we're looking for, times my universal gas constant R. I'll just write that down here, 0.08206. And then my temperature of 292. So now that I have all of these variables basically plugged in, I can just solve for N. I would just get a number for this, 0.410 times 5. Same thing, this 0.08206 times 292. Divide both sides by that, R times 292. And we are left with an N value equal to 0.08556 moles. So it asks us to round our answer to two significant figures. If I look at my numbers up here, I've got 3, 3, and 2 in my volume, so my answer should be in 2 sig figs. So if I was going to round this to 2 sig figs, that would be 0.086 moles. That's going to be what I plug in here for my number of moles. And then once I know my number of moles, then obviously I can solve for mass, something that we should be familiar with. So for sulfur hexafluoride, the molar mass is 146.07 grams per mole. So that's what I calculated for the molar mass, and I can just do a conversion here from moles into grams. That would look like 0.086 moles. And most likely I'm actually going to be using this number with more significant figures when I'm doing this first calculation, and then I'll round at the end. Shouldn't really matter in this case though. 0.7 grams over 1 mole. My units of moles will cancel out. And for my mass, I ended up with 12.5 grams. And then, since it asks us to round our answer to 2 significant figures, in this case, we're actually going to be rounding down to 12. So I would round this to 12 grams. That's sort of the newer rounding rule where we're going to be rounding to the even number. If that blows your mind or is really confusing, you can just round as normal as you probably have done the rest of your life. All right, I'm going to make a part 2 video. I think I'm running out of time on this one, so I'll make a part 2 video where I do the other more complicated version of this problem. But this is sort of the basics.